So this is instead about 2 older papers I did before while I was a postdoc at the University of Boulder in Colorado. The first one was by with Yifan Hong and Aaron Friedman, and the second one was with me. And they're both kind of talking about this relationship between quantum teleportation and string order, and this is what I want to talk about today. So I probably don't need this slide, but what is quantum teleportation? Well, you imagine there's usually 2 people, Alice and Bob, who here I've divided by this red dotted line. And Alice wants to get a qubit over to Bob. How do you do it? Well, Bob makes some entangled state, here a Bell state that I'm representing by this little kind of U shape, sends one of the qubits over to Alice. Alice does a Bell measurement on her qubit, which here I've represented by this projector onto these 2 Bell states. And note that here and throughout, I'm going to be using this notation here, where if I take kind of this U, which represents a Bell state, and I put some operator in the middle of it, that's like represents acting with that operator on one leg of that Bell state. So when I put P here for the different Pauli operators, identity X, Y, Z, this runs over the four Bell states. So Alice does a measurement in the Bell basis, and depending on her measurement outcome, which can be labeled by a Pauli operator P, what's going to happen is, so if the state psi starts here, you can kind of follow these lines along, go whoop, and then it ends up over here next to Bob. And so Bob gets the state psi, but actually he only gets it up to this operator P. And if Bob doesn't know what this P is and doesn't correct for it, actually, on average, he just gets a maximally mixed state. Nothing happens. And so it's very important that Alice communicates her measurement outcome to Bob so that he can apply this P to correct it himself and recover the state that he needs. And so the 2 points I want to point out here is kind of, the important part here is that they share the Bell state, and when 2 parties share a Bell state, they can do this teleportation. So there's kind of an equivalence I'm going to be using between sharing a Bell state and being able to do teleportation. And also it's extremely important that you have this classical communication to clean up what I'm going to be calling the byproduct operator, which is kind of this Pauli operator in this case. It's the undesirable operator that appears due to the randomness of measurement outcomes. And by the way, this first half of the talk at least should be very understandable, I hope. So if anything's not clear, feel free to ask in the middle. But now I'm going to be talking about a notion of kind of many-body quantum teleportation, which is kind of chaining this over long distances to teleport a qubit even further. So you can imagine if we have, say here, a few parties, so these endpoints, and then each of these circles represents some party. And so you can see that each party is kind of sharing entanglement with this neighbor, again, represented by these Bell states. If each of them now do a Bell measurement, what happens is that you establish, again, a long-range entangled state between the endpoints, and then this kind of entanglement is concentrated within these sites. So by chaining these protocols, we're able to establish long-range entanglement in finite depth. But again, notice that this long-range entangled state that you made depends on your measurement outcomes, which can be labeled by P1, P2, P3, and you have to know those measurement outcomes and communicate them to one of the endpoints so that they can fix them up. Again, that's very important. And so physically, this is kind of the basis of what people have called the quantum repeater architecture, where you kind of have a bunch of nodes that interact locally with each other. And by doing measurements and communication between them, you can establish long-range entanglement with this architecture. But also, this ability to just kind of shuttle a qubit over long distances is the starting point for measurement-based quantum computation, where in that case, not only do you want to transport a qubit over long distances, you also want to compute on it while you're doing that. So you want to apply gates to it while it's being teleported. So this is also an important kind of problem to understand when you want to think about measure-based quantum computation. And the basic question is, which quantum states can act as resources for teleportation? So in this case, our resource state was this initial product of Bell states shared between neighbors. We've shown that this can allow teleportation deterministically. What other states can also do this? Okay, so this is what I mean by teleportation throughout this talk. Is maybe it's a bad way of using the term, but I really mean this ability to establish a long-range entanglement over long distances, starting with some many-body state. Okay. So and more specifically, there's kind of 2 things I ask for when I want teleportation. The first thing is that, as I showed before, by measuring the bulk spins, I can entangle the boundary spins. So here I'm drawing some sort of spin chain with some boundary spins in red and the rest of them in blue. And the point is, by measuring the bulk ones, I can establish some entanglement between the endpoints. But again, in general, this entangled state that I make between the endpoints is going to depend on my measurement outcomes. And so I'm also going to want some way of efficiently and deterministically correcting these kind of, the byproduct operators that act on the state depending on the measurement outcomes. I want to correct them and map this onto some fixed entangled state. Okay, because again, in order to actually use this teleported state effectively, I need to map it onto a known state if I want to actually do something with it. And so this kind of deterministically is just saying, yes, I want, no matter what my measurement outcomes are, I want to be able to map onto this known state. Efficiently is not, I'm not being very clear what I mean by that yet. And in fact, this is really the crux of the whole classification. The way in which this byproduct operator correction occurs is very important for understanding resources for teleportation. Both the form of what the byproduct operators look like, so which operators I need to apply, and how do I determine which operators to apply based on my measurement outcomes. Both of these factors are very important. Okay, so my talk's about string order and teleportation. I told you about teleportation, now about string order. So this is kind of more from the start, comes from the condensed matter physics side, whereas if you wanted to evaluate some long-range order in, say, like in like an Ising chain, you would look at correlations of some long-range two-point correlation function of some charged operators, and this would indicate, you know, that you have symmetry breaking order or GHZ order or the like. A string order parameter is similar. You again have these two charged operators at the endpoint, but then in between them you have a big string of operators in between. So string order parameter is just kind of a long-range order under these long string-like operators. And so typically this is associated with symmetry-protected topological phases. So the original string order parameters came from, you know, studying the Haldane phase, AKLT chains, things like that. What I've drawn here is the string order parameter for the 1D cluster state, so it's much more general than just those old spin chains. But actually, I think we should stop calling it string order, because at least in this context of teleportation and MBQC, it comes in many shapes and sizes. It's not really just strings anymore. So here's, you know, what could be called a string order parameter of a 3D cluster state. Looks more like a membrane. You can have these big fractal objects, or this is, you know, or like these kind of weird cone-shaped object like this. So this is just a selection I got from some papers. And also I should mention that this one is string order in a topological phase, in the Tor code phase, and so string order is no longer just about symmetry protected phases, but also can be found in topological phases. But my point is, yeah, it comes in many shapes and sizes, not just a string, although in this talk I'm talking about 1D, so it will just be strings. And in general, a string order parameter is just some sort of extended object, which in the bulk looks like a symmetry operator, which might be like some fractal symmetry or something. And then you have some charge operators somehow decorating the endpoints. This is kind of a more general notion of string order. So yeah, string order is normally like a characterization of the physical phase of matter that your state lives in. But the point of this talk and of many papers, that, including these ones, is that it also tells you something about the computational properties of the quantum state that you're considering. And indeed, it's closely, for example, it's closely related to measurement-based quantum computation, which again, as I said, is like teleportation, plus on top of that, doing gates. On one hand, I am happy to say on the record that all MBQC resources, I shouldn't have put seems to be, are related to some kind of SPT order. And if anyone has a counterexample, I would love to hear it. But I don't know of any resource for MBQC, at least that allows deterministic computation that is not related to some kind of SPT order. I really would love to be proven wrong. And this kind of relation to SPT order, sorry, and SPT again is this symmetry-protected topological order, which is closely related to string order. This relation was originally showed by Akimasa Miyake in 2010, but it's been expanded upon by many, many works, including from Robert's group since then. On the other hand, also from Robert's group, they recently proved that string order is a sufficient condition for MBQC. So just having the presence of string order allows you to define all of the different ingredients you need to define a complete scheme of quantum computation. So like it tells you how to measure things, how to correct things, what gates you can do, and so on. This all follows just from the presence of string order. Very tempting to conjecture that MBQC is string order. You know, if you can do MBQC, you have string order. If you have and if you have string order, then you can do MBQC. And so one direction here was shown by Robert and Arnab, so I want to talk more about the other direction here, which is string order necessary for MBQC? So let me just quickly do a quick demonstration of why string order is related to teleportation, at least, not so much to MBQC, but to the teleportation. So here I'm drawing a one-dimensional cluster state, which you probably know how it's defined, but if you don't, it doesn't really matter. What matters is that it's some state of a 1D chain, and it has these correlations. Namely, if I act with X on all odd sites, or X on all even sites with Z on the endpoints, these two operators have expectation value 1 in this cluster state, or in other words, they are a symmetry of this state. So what can happen now is for teleportation, I'm going to measure out the bulk spins, and I'm going to measure them in the eigenbasis of these local operators that are acting in the bulk of these symmetry operators, so namely in the x basis. And when I do that, I replace each of these x's with the measured eigenvalue plus or minus 1. And so I get out a system where all the bulk spins have been measured out into some state, and the endpoints now satisfy these correlations, namely xx and zz, up to some signs. And again, these signs, -1 to the a, this a can be determined as the eigenvalue of kind of the symmetry operator that you measured in the bulk. So here, because this upper symmetry acts on sites 2, 4, and 6, I get S2 plus S4 x6, and so on. And from these two relations, you can actually uniquely determine what the state of the boundary is, and it's exactly this Bell state where I have a fixed, the Bell state with some Pauli operator applied to it, and this Pauli operator can be determined by the measurement outcomes I got in the bulk. Okay. And yeah, so not only does the string order show that kind of if you have these correlations to start with, by measuring the bulk, you end up with the correlations that describe an entangled pair between the boundaries. So we kind of have the entanglement generation part of teleportation, but we can also find the correction operators, and we find that they are simple, just Pauli operators, and we can determine what those Pauli operators are by some simple addition mod 2 of the measurement outcomes. Okay, so there's a simple classical processing I can do of all my measurement outcomes that will determine what this byproduct operator is, and I can then communicate that information to, say, one of the endpoints, and they can apply this correction. So I have both ingredients of my teleportation. I can make entanglement, and I can map that entangled state onto a fixed state, namely the Bell state. Okay, so this is kind of a hand-wavy argument of why. Well, I guess it's not hand-wavy, but for the simple case, this shows why string order gives you teleportation. Okay. Right. Okay, so now I need to slightly shift gears because I want to talk about my first result, but that first result came from a different context because it came from working with some people at Boulder, Andy wasn't on the paper, but he was on the precursors like Andrew Lucas, where they study Lieb-Robinson bounds. And Lieb-Robinson bounds tell you about how quickly information can spread throughout a many-body quantum system. So, for example, if I have a quantum circuit here that's evolving from bottom to top, so here I'm actually drawing kind of the Lieb-Robinson light cone in the Heisenberg picture. It's like, imagine some observable O at the end of my circuit. Which states from the start of my circuit can possibly influence the expectation value of this observable at the end of my circuit? That's kind of what this diagram is showing. And you can see if you kind of push O through this circuit, it's only going to be able to be affected by these states, because these ones are not coupled to this operator O through this circuit. So this slope of this cone is kind of called the Lieb-Robinson velocity, and it just tells you there's some finite speed of information propagation through our system. And okay, it's very trivial for quantum circuits, but you can also show it for general Hamiltonian evolution, that you kind of have this finite speed. And Lieb-Robinson bounds constrain teleportation. If I want to teleport a qubit to here, my qubit must have started somewhere in this light cone. Otherwise, there's no way its state could possibly influence this final state out here. So there's a statement that if you want to transport a qubit over some distance, you cannot do it faster than the Lieb-Robinson velocity. But that changes when you can do measurements. And in this picture, what the measurements do is they effectively let you kind of fuse light cones together to extend them. So now if I want to teleport a spin over to here from here, this now is possible because I do these measurements up here, and this kind of fuses these light cones such that this guy can influence the state over here. And so what they studied in this paper, the group from Boulder, is they showed, people might say, oh, once you have projective measurements, locality is totally thrown out the window. We don't have a Lieb-Robinson bound anymore. But they showed you do still have a Lieb-Robinson bound, but it's just augmented. And so now, rather than up here, the distance over which information can be transported is less than or equal to the Lieb-Robinson velocity times the depth of the circuit, t. Here, it's that same thing, but you have this extra factor of 2m, where m is the number of measurements, which is showing that each measurement you do allows you to kind of chain together more light cones and send your qubit further. Okay, so this was kind of the subject of this paper. And here we're thinking of teleportation as a way that allows us to transport the information of a qubit further than what is possible unitarily, and for that we need measurements. So this is the context we studied in this paper, and we just said, suppose you implement some protocol that teleports k qubits, we can think of 1 qubit for now, faster than what you can do with just unitary dynamics, therefore, in a way that overcomes the Lie-Robinson bound. So I kind of imagine I have some spin chain down here, and over on the left I have some qubit chain, some qubit I want to teleport, and I do something, I don't know what it is, but at the end my qubit ends up over here. And I know that I must have done some measurements because kind of if I look at the Lie-Robinson light cone of this guy, it only extends this far, and so some sort of measurements must have happened in this box. And so the question is, what could I possibly have done? And what we prove is that the only thing that you could have done is made a string order and measured it. So we show that if this protocol succeeds, then what you must have done in this box is prepare a state. That state has string order parameters, namely kind of 2 complementary string order parameters for every qubit that you want to teleport. And again, in 1D, string order is basically synonymous with symmetry protected topological order. So I prepare an SPT order, I measure the string order parameters, and then I apply feedback according to the measured eigenvalue of the string order parameters. So this picture I showed you a couple slides ago about how string order lets you do teleportation, we prove that that is the only thing you could, if you ever somehow manage to teleport a qubit, you must have made an SPT at some point. Now there are some important assumptions that went into this work. First of all, there's just some technical ones, like you don't on the kinds of measurements we do, but I don't think they're that important. The real important assumption is this one: is that we assume the byproduct operators, namely the corrections you have to do at the end, are Pauli operators, and that all the classical processing you do of your measurement outcomes to determine that byproduct operator is linear. Okay, so this goes back to what I was saying, how in the definition of teleportation, the way that you do the correction at the end is very important in classifying teleportation. And so in this case, we picked the simplest case where the recovery is always Pauli's and the classical processing is always linear. But in that case, we're able to prove that teleportation implies string order. Okay, so this is the first result. And this is kind of a converse, and this shows, at least up to these assumptions, teleportation and string order are equivalent. Okay, and I don't want to explain how the proof works because it's very technical and I don't understand it. But basically, the main technique we use is something called the Steinspring dilation, which is you kind of think of measurement in a unitary way. So rather than measuring a particle, you couple it to some ancilla, and that's kind of equivalent to measuring it. And then later, you can do some unitary control on the state of that ancilla to figure out your correction operators. So when you think in the Steinspring picture, the whole measurement and feed-forward process can be thought of unitarily, and that's just very technically useful. In particular, you can say, okay, let me take the final kind of x acting on where my qubit was teleported to. So this is like the logical operator according to my qubit. I can pull it through this big unitary circuit, and it turns out to give me a string order parameter. And I do the same thing with a logical Z, it gives me the other string order parameter. So we basically prove that no matter what you do in the middle, something like this is always possible. You can always recover two complementary string order parameters that you measured to make the teleportation happen. Okay, yeah, that's all I'll say about that proof. So now I want to move to part 2, but I think part 2, unfortunately, just due to the technology needed, might lose some people. What this is basically a story of is an example I found of a resource that does teleportation that doesn't fit anything that I ever understood, and I spent a long time trying to understand it, and it led to some very interesting insights. Unfortunately, to describe this example, I need to introduce matrix product states. I'd rather not if I don't have to, but I have to. But actually, in this case, maybe we're prepared to understand them in a unique way. What a matrix product state is it's a way of decomposing a many-body state into a bunch of kind of small building blocks called tensors. So here, my state is defined. I have these matrices A, S, for where S runs over my basis. So for a qubit, I have A0 and A1. Each of these is a D by D matrix. D is what we call the virtual dimension, and you kind of define a state in this way. But in the picture we're talking about, what this definition is kind of like, hey, if I take my state and I measure out all the bulk spins, what is the spin, or what is left over for the boundary spins? In this case, it's exactly determined as a Bell state with this product of these A matrices applied to one of the qubits. If you remember this notation I've been using, this is like a Bell state with some matrices applied to one of the qubits. This is maybe an unconventional way of thinking of a matrix product state, but in this case, yeah, it's just a state that tells you exactly, hey, if you measure me in this basis, this is the state that's going to come out at the endpoints. Okay, maybe that's a weird way to say it. If you don't, if you haven't seen these before, what really matters for the talk is it's just a way of building up a state from small pieces. It's a very convenient way to represent and describe some states. And it's a very natural language for string order and teleportation. So for string order, what can happen is you can derive it from a local symmetry of the tensor. So imagine this local tensor satisfies this, which is like applying u to this physical index is the same as conjugating kind of with v in this virtual space. And if you have this, then you can take your MPS, which is again represented by this diagram, insert VV dagger everywhere, which does nothing. Then I can pull these VV daggers up to the physical space as these U operators, and what I've derived is exactly a symmetry of the state. I act with U on all the bulk spins and VV dagger on the boundaries. This is the symmetry of the state, this is string order. So in MPS, string order can be derived from local symmetries of the tensor. Teleportation, I kind of already alluded to, is also very easy to understand in MPS. Namely, if I measure all these bulk spins out, what that does is contract these legs, and I end up with this state between my boundary particles, which has this form. It's exactly a Bell state with these matrices applied to one of the qubits. And what you can notice is that if all of these S's for all S are unitary, then this is just some unitary applied to half a Bell state, so it's still a maximally entangled state, right? If you take a Bell state and you apply a unitary to half of it, that does not change the entanglement. And so there's this picture, which was actually developed by people in the audience here, like Jens, and I don't know if David Gross is here. But it's saying, in some sense, you can think of teleportation as happening as unitary evolution in the virtual space of a matrix product state. Okay, so this was a very powerful insight they had a long time ago, and it's been, I'd say, every kind of teleportation I can think of can be put in this framework. Yeah, so kind of this idea of having unitary tensors in your matrix product state, and therefore like it kind of forms a unitary channel that your state is being transported across. That's a very good picture. So now I've told you what MPSR is, I can tell you about my puzzling example. So this puzzling example came from a paper by Torsten Wahl back at MPQ, where they studied exactly this problem. If I take an MPS and I measure all the spins, when do I get entanglement between the boundaries? And they completely classified when at least this entanglement part is possible. They didn't talk about the correction part, only the entanglement part. And they gave this example, which is again, here I'm defining a matrix product state by defining the two matrices that define it. Unfortunately, I can't give you any more insight to what the state is. It's some matrix product state. But you don't really need to, it's just some state. And they showed that by measuring the bulk spins of this matrix product state, you can create long-range entanglement between the endpoints, namely that of a maximally entangled qubit pair, a qubit Bell state. So I saw this example while studying for this other project, and it was very strange to me for many, many reasons. First, normally, at least in this picture, the entanglement that you get out from measuring a matrix product state has dimension equal to the bond dimension of your matrix product state right here, which is this big D. Here, these matrices have dimension 3, but what they showed is that you only get entanglement of a qubit, which is 2, and 2 is not 3. Also, I tried to explain that in MPS, the way teleportation works is you have this kind of unitary evolution in the virtual space, but these tensors are not unitary. There's no basis in which they're unitary. There's no subspace or subsystem on which they act unitarily. There's just no, they're not even full rank. So how is teleportation occurring? Next, can we understand the teleportation in terms of symmetry or string order or SPT order? And what they showed in this paper is that this state only has one Z2 symmetry. And what I've tried to explain so far is that for teleportation, you need two symmetries, two kind of complementary symmetries, which after measuring give you the correlations you need for entanglement. This one only has one symmetry. So how does it do teleportation? And finally, they didn't address at all, is there a way to actually compute kind of, the byproducts efficiently and do the correction at the end of this state? So this state, I've tried to put you in my frame of mind, but this just rocked my world and I didn't understand it. And to understand it, I eventually had to create a new kind of tensor network. And I called these SIMPs. So again, this is a matrix product state that I defined before. Here I wrote the equation for periodic boundary conditions, but it's basically the same thing. You define it in terms of these tensors that you stick together. This is a SIMPs. So up here, so they look very close at first, but you can see here that here, what I have is like the first matrix depends on S1, the second one depends on S2, last one depends on Sn. But here these matrices have two indices, so they are informed by the state of two particles, and I have B, S1, S2, B, S2, S3, and so on. And you can see that each index, like S2 for example, is split across two different matrices. Okay, so that's where this name split index matrix product state comes from. I take this index and I split it across two matrices. And I again take those trace matrices and that gives me my state. So they're very close, but slightly different. And if I was going to draw a picture of this, I would first define this delta tensor, which basically takes a state coming in the top and copies it to the left and right. So it does exactly the splitting of the index for me. And then I now have this 4-index tensor, Bij, as opposed to the 3-index one up here. And so it takes two inputs and then it gives you out some matrix. And so then I kind of stitch these things together like this. So you can see here the index S2 is kind of split across these two tensors. And that's exactly this S2 appearing twice in this equation. And now these B's also, are some matrix, and I'm going to call the size of these matrices the virtual dimension of the sim, so I'll label it as chi. So the class of states that can be efficiently captured by MPS and SIMs are equivalent. So I'm not reaching new kinds of states by writing this representation. But what happens is that when you write an MPS as a SIMs, you can more clearly reveal many features of the state. Okay, so it's just an alternative representation that helps you understand certain things much better. Okay, I'll go through this very quickly. I showed a few kind of fundamental properties of SIMs. So for example, how do you convert between an MPS and a SIMs representation? I'll briefly say the way you go from an MPS to a SIMs is kind of, you take your MPS matrices, you multiply them by a projector onto the row space, and then you define your SIMs tensor in terms of these matrices and these projectors. And to go from a SIMs to an MPS, you just kind of you kind of cut the tensor in half, do some SVD, and regroup things. But what's important here is that, according to this equation, when you go from MPS to a SIMS, something non-trivial is only going to happen if your MPS tensor is not full rank, because that's when this P is going to be not the identity. So only when you have these matrices AI being not full rank is the SIMS representation worth looking at. And this seems like a very fine-tuned property that isn't going to hold generically, and so it seems like SIMS wouldn't be useful. But what I was able to show is that certain physical properties, like certain symmetries and local constraints, guarantee that your matrices are not full rank, and therefore a SIMS representation may be useful. Okay, so this is not a fine-tuned property. And for those of you who know MPS, there's something called the fundamental theorem of MPS. So I proved a fundamental theorem of SIMS, which is just if you have two representations of the same state, it tells you how kind of the defining tensors must differ. So this is kind of similar to the MPS relation, but a bit different. And this helps you understand symmetries in the states very well. And quickly, some examples of SIMS. 1D cluster state. Okay, I will define it now. You take a plus state and you put controlled Zs between all neighboring pairs. What this does is it's like a sum over all bit strings, and it gives you a -1 factor for every pair of neighboring ones. If you were to write it as an MPS, you normally write it like this, which you can kind of see how that does this if you stare at it long enough. But the SIMS kind of directly encodes the structure. It just says, hey, when you take this product of matrices, look at all of your pairs ij. If they're both equal to 1, give yourself a sign of -1. So it kind of more clearly communicates the structure. And you see here, as an MPS, the cluster state is bond dimension 2, as a SIMS state is bond dimension 1. Similarly, a GHZ state can be written like this as an MPS, and as a SIMS, you write it just in terms of this bond dimension 1 delta tensor. And maybe a more interesting one, this state is can be thought of as like a symmetry breaking state between a trivial phase and a non-trivial SPT phase. So this kind of actually breaks a non-invertible symmetry in modern language. It turns out to be represented by some bond dimension 3 MPS and a simple bond dimension 2 SIMS. And again, by staring at this representation, you can get a lot more intuition about what this wave function looks like than you could by staring at this MPS. But let's go back to the puzzling example that I started with. So this is the example from this paper from Torsten Wahl. And if you turn it into a SIMS, it has this very nice form. So here, I have a qubit, so I have to define four matrices, B00, B01, and they have this form. So they're all Pauli matrices. So what I want you to notice is first, these are unitary. While these ones were not unitary, these are unitary. So in the SIMS representation, you do have unitary evolution. And second, the bond dimension of the SIMS is 2, whereas it's 3 in the MPS. So this is going to solve two of our questions. Our first question was, how are we having teleportation without unitary evolution? It's because the unitary evolution is not happening in the virtual space of an MPS, it's happening in the virtual space of a SIMS, where the evolution is unitary. Second, why do we teleport only a qubit and not a qtrit, even though the bond dimension is 3? It's again because the important bond dimension is that is the SIMS, and that is bond dimension 2. So that's why we only teleport a qubit. So let me just say this teleportation a bit more clearly. So again, this is how my tensor is defined. If I take my state and I measure all the bulk spins, I end up with this state between the boundaries, which has this form, again, as usual. But now using this definition, you can say that the product of B's is equal to some Pauli matrix, which can be determined, again, efficiently from the measurement outcomes. So teleportation can be understood, again, due to unitary evolution, and it's in the bond dimension 2 Sims virtual space. That's why you get a qubit out. So this answers the first question. And something very interesting I want to point out, and this is why this example could not be captured by the first part of my talk, the classical processing you need to do to figure out the byproduct operators is no longer a linear function of your measurement outcomes. You have to multiply S1, S2 plus S2, S3, and so on. So this violates this assumption of linear classical processing. And that's why this state does not fit in that paradigm. So this is kind of what I'm trying to say about how important it is how you deal with the byproduct operators. Even though it's just Paulis, it still differs in the fact that in kind of how we compute these Paulis. Okay, now let's talk about the symmetries. The sims can also help us see the symmetries. From this tensor, we can immediately, without even thinking, write down these symmetries. At least if you're used to looking at MPS, you can write down these symmetries of your local tensor. Because this is saying if I conjugate these matrices by x, I get a minus sign only in this case because I anti-commute with this z. So I get a minus sign only if both physical indices are in the one state, and that's what this controlled z checks. And if I conjugate by z, I get a minus sign only if the first index is in the one state, and that's what this z does. So I can very easily, just from staring at this, derive these symmetries. And then again, as I did with MPS, from these symmetries of the tensor, I can derive symmetries of the state. So I take these pairs of x's, I insert them into my state, it does nothing. I turn these x's into these cz's using this relation. And now I do a little trick where I kind of pull these cz's through this copy tensor, this delta tensor. And the reason I could do that is that, if this index is in the state 1, then this one is as well, because the whole point of this tensor is that it enforces all of the incoming indices have the same value. So I can kind of pull these cz's up. And so we've derived a string order parameter, a symmetry, but it has a fundamental difference from all other string order parameters which have been defined until now, in that the bulk is no longer a product of local operators. It's rather like a finite depth quantum circuit of these controlled Z operators. Okay? So this is much different from conventional string order, and we'll see it totally changes the physical properties of the state. Similarly, with this relation, we can derive a simple on-site symmetry, which is Z, and this is the symmetry that they saw in that Torsten Wahl paper. So, they were able to see the on-site symmetry, but the MPS technology is not well equipped to see these non-on-site symmetries, whereas the SIMS representation is extremely natural to capture these non-on-site symmetries. I would say, I don't think there's any way you would have ever stared at the MPS and realized that the symmetry is there. I can't even think of a computational way of doing that. I guess you could vary over all MPOs, but it's just not feasible. Whereas for the SIMS, it just immediately pops out. So without writing this down, you would have never seen this symmetry, I think. We do have symmetries, but one of them is what I call non-onsite. And I just want to quickly reflect back to the teleportation. Notice that in calculating this Z byproduct, I have this non-linear function of my measurement outcomes. This is nothing more than the eigenvalue of this string of CZs. Because even though this is a non-onsite operator, I can measure its eigenvalue by doing local Z measurements, and then I just have to kind of multiply them to figure out what the eigenvalues of these CZs would have been. So the fact that you have a non-onsite symmetry is why we had this non-linear classical processing. Okay, so now I want to take just a quick brief intermission to talk about the physics of these phases with non-onsite symmetries. So as usual, we have some symmetries. We can consider perturbations that respect these symmetries, so we can define phases of matter. What are the features of these phases? Well, first off, as usual, we do have boundary degeneracy. So if you have some Hamiltonian in the bulk that respects the symmetry, we're going to have some degeneracy near the edges. This is conventional. This is true of normal SPTs, and it's true here as well. What we do not have is entanglement spectrum degeneracy. So if you kind of cut your state in half and compute the reduced density matrix, normally for an SPT, all the eigenvalues will be, say, twofold degenerate. So your density matrix kind of has this form. But this is not true in this case. You do not have entanglement spectrum degeneracy for these SPT phases with non-onsite symmetries. And this is kind of shocking because alongside this virtual evolution picture of MPS, people would often say that when doing MBQC or teleportation, you're kind of encoding your state in this degenerate entanglement spectrum. But we don't have that here. So that picture does not hold here. Finally, for the experts, you'll know that for an MPS representation, we have this result we're kind of, if you take a tensor away from the fixed point of the phase of matter, it kind of looks like the fixed point tensor with kind of what we call this junk part. We're able to prove such a result in this context as well, but that's just for the experts. To end, I want to talk about one more example of the SIMPS, which not only can it teleport, it can also do universal measurement-based quantum computation, at least on one logical qubit. And okay, this is the SIMPS. You don't have to think about where this came from. I just thought up of something that at least has one of the symmetries being not on site. And again, I won't go into details, but you can prove that the SIMPS generated by these tensors is universal for MBQC. And the way you use it, one way of using it is you first measure all the odd sites, and then you're going to have a cluster state on the even sites up to some local unitaries, depending on your measurement outcomes, which you can correct. And then you can just use that cluster state for MBQC. But what's interesting here is that, this is, as far as I know, the first deterministic protocol of MBQC that requires nonlinear classical side processing. Please correct me if you think I'm wrong. It's also the first MBQC resource without entanglement spectrum degeneracy, and I'm fairly sure about that one. And so the SIMPS was very helpful to find these new examples. And I want to say this nonlinear classical side processing is very interesting because there's some very fundamental connections between MBQC and things like contextuality. And I know that in those papers, it's very important to have an assumption that all the classical side processing is linear. So here's an example that can only do MBQC with nonlinear side processing. What implications does that have for these fundamental examples? I have no idea. Yes?
How does this fit with reject methods?
That's not deterministic. You could get like the all zero outcome and then you have no cluster state left, or like, no state. So I'm saying, I'm saying no matter which measurement outcomes you get, it always works. So that's why also like these AKLT state protocols have a similar thing. Those are also not deterministic. Of course, in the limit of large system size, they're going to work with high probability, but it's not deterministic in the same way as this. That's it. So over this talk, I've tried to strengthen the conjecture between teleportation and MBQC. I've proven in one case the reverse direction that teleportation implies, between teleportation and string order. I've proven in one direction that teleportation implies string order, and I've shown that if we actually want this conjecture to survive, we have to be more general about what we mean by string order by allowing these non-onsite string order parameters. So a few open questions. Can we use similar techniques to show that if you want to do fault-tolerant MBQC or fault-tolerant teleportation, which is teleportation that works even in the presence of errors, do you need to have some sort of deformable string order like higher form symmetries, which is the case in the 3D cluster state? Our result shows that teleportation implies string order. But from Robert's result, Robert and Arnab, it's known that string order implies MBQC. So does this mean that within our assumptions, every resource state for teleportation also allows MBQC? I think that would be a very interesting result because we normally think of teleportation as like, the first stepping stone to MBQC, but then you have to prove more on top of that to make the MBQC work. But this seems to imply that actually whenever you can teleport, you always have MBQC as well. That would be interesting if we could show that. I've talked about these ways of generalizing and classifying teleportation by understanding the byproduct propagation. There's still lots of ways to generalize this, like having CZ byproducts or more complex classical processing. Can we find such examples, and does every kind of generalization like this lead to a new kind of string order? And finally, I'd love to do more with SIMPS. I have more examples of what you can do with them. They're very good at capturing constrained spin chains, many-body scars, Hilbert space fragmentation. You can prepare them efficiently in finite depth, but I think it's a cool application, especially in this context. So that's all. Thank you.